Hi, everyone. Here we present our latest work, Structure from Motion with a Non-Parametric Camera Model, also called GenSfM. Structure from motion is a method that takes a set of unordered RGB images and estimates the point cloud of the 3D scene as well as camera poses. Standard SFM pipeline relies on wisely choosing specific parametric camera models to describe camera parameters and model camera distortion. Failing to choose the correct camera model will result in failed reconstruction, which is rooted from a wrongly modeled distortion. Our work, GenSfM, aims at developing an incremental SFM pipeline that works for generic camera models and remains robust to severe radial distortions. There have been several works targeting at non-parametric camera model. For example, the work Implicit Distortion Model proposes to model the calibration map via pointwise focal length. As for full SFM pipeline, 1D radial SFM achieves calibration-free by using only radial alignment constraint, which only requires the 3D point to project onto a radial line passing through the image point. However, this approach only recovers 5 degrees of freedom camera poses. Our pipeline instead is capable to recover full 6 degrees of freedom camera pose. One of the main features of our work, GenSfM, is that we represent the calibration map in a non-parametric way with cubic spline. It is represented by a set of control points between theta and r. During projection, we find the image point radii corresponding to the viewing angle with this calibration map, while when the reverse mapping is needed, for example during triangulation, we find the viewing angle with Newton's method. Unlike the previous parametric model, this enables smooth, invertible, universal modeling of diverse camera distortions benefited from its flexible shape. Another feature is an adaptive partial calibration scheme. In order to remain robust to bad distortion estimations due to sparse data points, we only calibrated the region where there are sufficient constraints. We update the calibration map when the calibrated area grows. Let's see an example. At early stage, we only have sparse data points and thus bad calibration estimation. However, with more images registered, we are able to improve the calibration estimation and also the reconstruction. This feature helps us to bootstrap a more complete calibration map and scene geometry. Here is an overview of our framework. Without known calibration or specific parametric model, we collect initial 2D, 3D correspondences with radial alignment constraint as images iteratively registered. To the 3D model, we progressively calibrate the camera by fitting a non-parametric distortion map, which is initialized with implicit distortion model. After radial initialization, we adopt implicit distortion model to register new image to the model. This method could jointly offer full camera pose and partial pointwise calibration map. Now, with the pointwise calibration map recovered, we need to consider calibration map updating. On top of previously mentioned calibrated area recognition, we also need to robustly fit the spline. We adopt ransack sampling scheme for the control point selection. The calibration map is updated when calibrated area grows. We need to deal with combinations of calibrated and uncalibrated regions during both triangulation and bundle adjustment. For triangulation, we iterate through all possible cases that meet the 3 constraints requirements and keep the points supported by at least 4 constraints. For bundle adjustment, full reprojection error is applied to calibrated area, and only radial reprojection error is applied to uncalibrated area. The calibration map is jointly refined during bundle adjustment. We keep the theta values for the control points and optimize their error values. In experiments, we evaluated both the calibration ability and reconstruction quality. We compare with CalMap with various parametric camera model as our parametric baseline and also 1D radial SFM with pose upgraded by implicit distortion model as our non-parametric baseline. Let's first see some challenging reconstructions from catadioptric or fisheye images. In general, compared to other methods, our pipeline achieves much cleaner reconstruction with sufficient points. The calibration map quality is evaluated on controlled checkerboard. We achieve similar results with parametric models, demonstrating our good calibration map quality. The full pipeline is first evaluated on ETH 3D dataset. With mostly pinhole-like images, we achieve the best or the second best pose accuracy on all the scenes. The general quality of the reconstructed point cloud is also satisfactory. Since the real strength for our pipeline is the reconstruction on distorted images, so we manually added a fisheye distortion on ETH 3D datasets. This time, the advantage of our pipeline becomes significant. We have clearly better results for both point cloud and camera pose compared to all our baselines. For camera poses, we remain comparable performance against the original dataset while other methods significantly struggle from distortion. More reconstruction results from large field of view images could be found here. To justify our calibration map recovered, we used it to undistort those severely distorted images like catadioptric and fisheye. As we could see, the undistortion goes quite well. We hope this work could help incorporating a much wider range of cameras into computer vision tasks. The code can be found via this link. Thank you for your listening.